All right, so let's take a look at our lesson for today. So today we're going to be working on algebraic techniques for finding limits. And actually, this is the technique that we use probably 90% of the time. This is the one that we normally use, is the algebraic techniques. Last time we looked at numeric techniques where we use a calculator or a table, and we also looked at graphing, doing limits by graphing. So this is the most common one here, algebraic. So before we get into exactly how to, let's look at some of the different laws that we are allowed to use to rewrite the limit, to perhaps break it down into pieces to make it easier for us to work. So we have the first law, which tells us that if we're doing the limit of two different functions that are being added or subtracted, we are certainly allowed to split them. To, like, the first one, do the limit of the first one, and then plus or minus the limit of the second one. So that is perfectly acceptable, and sometimes it's quite necessary for us. Likewise, when we're dividing, we are allowed to do those separately. So we can take the limit of the first one and divide it by, find that number or letter, and take the limit of the second one, divide by that. And of course, obviously, we can't have the denominator be 0, or if we do, we know that that means that the term or it's undefined, right? A number over 0 is undefined. We'll just come back over here to number 2. It's listed. So we are allowed, C we know is a constant. It's just like a number, like 5 or something. We are allowed to pull that out front and then take the limit of that. That's an okay thing to do. The next one is if we have like a function raised to a particular power, we are allowed to take the limit of the inside and raise the whole thing to that power. So these are just things that we can utilize if we need to. Down on that bottom line, if we have two functions that are being multiplied together, we are allowed to do them separately. We take the limit of the first one, get that value, and then multiply by the limit of the second one and get that value. And the last one that we're going to look at is this nth, like a radical, the nth radical, the third or fourth radical, whichever one it ends up being. We are allowed to pull that outside the limit as well. These are similar. They're basically the exponential, whether it's a whole number or a fraction. These are kind of similar, those two techniques, where we are allowed to pull it outside. So that's just some background information, some laws that we are allowed to use as we're working through algebraic limits. So let's kind of get to the basics, the meat of this lesson, and that is, how do we do this? How do we find limits algebraically? Really, I have like little 3 stars here, and that basically is telling, truly, these are the only 3 things that you can do. Sometimes students get really overwhelmed. How do I do this limit? What do I do? Okay, step 1 is going to be taking, let's just kind of note this a value, okay, as x goes to a. We're going to take that value and we're going to substitute it into the function, and if that number, if it exists, we are done. This is ideal. We would love that to happen. If I simply plug in a to the function and I get like 5/2, we're done. If it exists, that's the first way, and really, that's really ideal. Does that happen very often? Not really, because that's really pretty easy, right? Just plug in the number and you're done. All right, so that's the first thing that could happen. So the second thing is actually the most common thing. Number 2 is the most common thing that's going to happen. When we substitute that a value into the function, we get something called this 0 over 0 or infinity over infinity. And this would be or infinity over infinity. These two things are called indeterminate forms. And I'm probably spelling the word wrong. Indeterminate, okay. I apologize if I'm spelling it wrong. Indeterminate forms. And so what does that mean? What does the word in English mean? Indeterminate. It means that we cannot determine what the value is by just looking at it. Okay, there is a value, but we have to kind of dig in. This indeterminate form, this means, when you see this, what I want you to think is that this means keep going. That's what I want you to think. When you see it, I want you to think you need to keep going. You need to keep going and use ways to rewrite. Use algebra or trig to simplify or rewrite. Because what's happening is, and this is kind of fun, it's like a little treasure, right? It's kind of buried in there. There is an answer. We just don't know what it is right now. But we can do some work and figure it out. Okay, so this type 2 is the most common type that you will encounter, is where you plug the, a value in, you get 0 over 0 or infinity or infinity. That means keep going. That means do something algebraic or trigonometric to change the way that it looks. And these are things that you could try. Factor and reduce is one option. You could multiply by the conjugate over itself. And this needs to be, you can only multiply by 1, right? You can't multiply by anything else. You can only multiply by the number 1. So that means you have to multiply by the conjugate over itself. Or you might just need to find a common denominator, maybe fix your complex fraction. So these are basically the top 3 things that you would encounter. Probably 80% of the time, it's going to be one of these 3 things that you would need to do to kind of dig in and find that limit. The third thing that can happen when you're finding limits algebraically is that you get a 0 in the denominator, but a number in the numerator. So for example, like, what does this mean? It means a 0 in the denominator, not numerator and denominator. That's called an indeterminate form. I'm talking about like some number over 0. Example, like 3 over 0 or negative 7 over 0, something like that. That's the third type. And that one isn't as common as the second type. And what that means is, so let's just write ourselves some notes. This means there is a vertical asymptote at x equals a. That's what that means. A number over 0 means there is a vertical asymptote at x equals a. So what do we want to do? What we want to do is we want to look at the behavior at the vertical asymptote. Let's say the vertical asymptote is like here. Let's call this A. Okay, so here's an example here to the side. That's A. We've got a vertical asymptote. So we know with vertical asymptotes, we're not allowed to pass through that asymptote. So we've got to look at the behavior of the function. So as we are looking at, as x goes to a from the right, so perhaps it's going up like this. As x goes to a from the right, it's headed to positive infinity. And perhaps in this example, as x goes to a from the left, it's headed to negative infinity. That's going to give us our answers, right? So if it were going to positive infinity as x goes to a from the right, in this example, this one, so this is as x goes to a from the right, this tends to infinity. And this one down here is as x goes to a from the left, this tends to negative infinity. And we would say that that limit doesn't exist, D and E. Just an example of what you might encounter when you have type 3. Type 3 is where we have a number, some number in the numerator and 0 in the denominator. And that is all that can happen, ladies, either 1, 2, or 3. So what is the first step for finding a limit? You need to plug A in. You need to plug A in and figure out which one of these 3 types do you have to work with. And after you plug A in and figure out which one to work with, then you would do those steps. If it's type 1, yay, we're done. If it's type 2, keep going. If it's type 3, look at the limit from the left and the right of that vertical asymptote. Okay, so I'm going to pause here for a second and make sure we're doing okay. Are there any questions so far? But this is just the total big concept that we're dealing with. Okay. All right, so let's go into our first example. Our first example is asking us to find the limit as x approaches 2 of the average rate of change of f of x from 2 to x. Okay, so we have to dig back into our memory. We did average rate of change earlier this semester. I can't remember which unit it was in, but we did average rate of change. So we need to do that first. This is a calculus thing. Average rate of change is very common in calculus. So I'm just going to do that first, the average rate of change. I'm just abbreviating rate of change. So if you recall, the formula is f of b minus f of a over b minus a. That's our formula for average rate of change. And in this example, here is our function. Our function is right here. That's our f. And this is our a, and this is our b. Okay, so those are the parts that we need for this formula for average rate of change. So let's work on that. So f of a, f of b minus f of a. So b is x. So that gives me x squared plus 3x minus, okay, so that's f of b. And we just talked about b is x. So that means that that's what I get here. That's f of b. Minus f of a. So that would be 2 squared plus 3 times 2 over. So again, this is a right here. A is 2. And so I'm plugging in a 2 everywhere there's an x. I'm using my formula. Over b minus a. So b is x and a is 2. This is simply plugging into the average rate of change formula. Okay, how are we doing? Does it bring back any memories? I'm hoping. All right, so my job now is to take that formula and simplify it. We need to, get it to looking kind of normal. That doesn't look very normal. So this is the same thing as, let's see, I've got x squared plus 3x minus, let's see, 2 squared is 4, 4 plus 3 times 2 is 6, 4 plus 6 is 10 over x minus 2. All right, so that's my first step, average rate of change. Now they want us to take the limit as x approaches 2. So the limit as x approaches 2 of that x squared plus 3x minus 10 over x minus 2. Okay, so I'm going to pause here for a moment. So now we've got the average rate of change formula all, prettied up, and we're getting ready to take the limit as x approaches 2. So what's my first thing? Doing algebraically, I plug in the 2. And I get 2 squared plus 3 times 2 minus 10 over 2 minus 2. That's what I get. So I do my arithmetic. So that's what, 4 plus 6, that's 10 minus 10. I get 0 over 0. That is type 2, and the most common type that we will encounter. The most common type. So what we need to do now that we know it's a 0 over 0, which is an indeterminate form, please know that 0 over 0 does not necessarily mean 0. It could be anything. It could be, really could be anything. We can't make any assumptions here. So we've got to look at the function that we're dealing with. So let's go back and let's just kind of look at this and think about what kind of things could I do to that to change the way it looks. Multiplying by the conjugates would seem to be a bit messy. I don't really want to kind of get into that. That would make this a gigantic thing. What about factoring? Let's see. I'm going to try to factor. I want to take the numerator and see if I can't factor it and see if I can't do something to make this look different. So that's our goal. We need to rewrite this function so that it doesn't look like that, because when it looks like that, we get 0 over 0. So the answer is in disguise. We don't know the answer yet. All right, so I'm going to factor. the numerator. Let's see, we got an x and an x. The back sign is positive, so that means those are different. Let's see, multiply to get 10 and subtract to get 3. What would that be? A 2 and a 5. Okay, that works. All right, so what do we see once I factor the numerator? What do we see we can do? Absolutely, we can cross out the x minus 2. So that's what I'm going to do. I'm going to cross that out, and I'm going to rewrite this and do the limit again. So this is going to be the same as x plus 5. Okay, so now we go back to step 1 where we plug the 2 in. That's what we do. We plug the 2 in, and we get 2 plus 5, or 7. So this time, 0 over 0 was 7. So you can't really predict what it's going to be. All right, so that's an example of two things really. Finding average rate of change is a reminder from our previous work, and doing our limits algebraically. All right, questions so far? All right, so let's move to the second page. We just have more examples. We're just going to continue to do more examples to try to get a little bit more comfortable with what we're doing here. All right, so let's go to page 2. Now, number 2, if you look at that, this is a classic limit law problem. Let's just write this up here. When you see problems where you're given just these random values, like the limit as x goes to 3 of f of x is 2, the limit as x goes to 3 of g of x is 0. Okay, that's kind of weird. What this is this is a classic limit law problem. What does that mean? That means that you have to use limit laws to work this out. Okay, that's what that means. The limit laws that we went over at the very first part of the lesson, those limit laws, that's what you have to use. You've got to use those, because that's how this type of problem is designed. This type of problem is not designed for you to plug this in your head and come out with a number and be done. That's not going to be sufficient work for this. You can't just say, oh yeah, I know that's going to be 2. No, you can't do that. You have to actually use a limit law. At least one limit law. So the requirement, I'm just going to write this out to the side. It'll be the same thing for next year. The requirement, use at least one limit law. Use at least one limit law. Okay, so we can see that we have an addition of functions. So let's use that first limit law, the addition one. So the limit as x goes to 3 of f of x plus the limit as x goes to 3 of g of x. Okay, so that meets the requirement. I used one limit law. Now I'm going to look at the information I'm given, and I'm going to see if I can do a straight substitution. So the limit as x goes to 3 of f of x, I know what that is. I have it up there. It's a 2. And the limit as x goes to 3 of g of x, I look up there. I see that. I know what that is. That's a 0. So my answer is 2 plus 0, which is 2. And that's the amount of work you're expected to show. You're expected to show the limit law, and then you're expected to plug in from any information that you have been given or information that you can determine. All right, how are we doing on the first one? Okay. The second one, you can see this is a division one. So I'm going to use the dividing limit law. So we've got the limit as x goes to 3 of f of x divided by, I'm just going to put it in a fraction form, the limit as x goes to 3 of g of x. Okay, so that meets my requirement. I have used one limit law. Wonderful. Now, what am I supposed to do? Now I'm supposed to take the information that I'm given and substitute it in. We're substituting into our expression. So let's see, the limit as x goes to 3 of f of x, that's 2. The limit as x goes to 3 of g of x, that's 0. Oh, this is a type 3. This is a type 3 from the last page. Now we would, if we knew the functions, we would consider the limit coming from the left and the limit coming from the right, but we don't even know anything but two values. Unfortunately, this is one of the rare times when we have something that looks like this, we're just going to say D and E. That's all we can do. We can't do any more exploration. We can't do any more, figuring out stuff. It's just, well, that doesn't exist. Okay. All right, and that's the second one. We doing okay? All right, the last one. So that's a multiplying one. So I'm going to split it by multiplication. I'm going to do that limit law. So the limit as x goes to 3 of x squared times the limit as x goes to 3 of f of x. Okay. So now this particular kind of problem can sometimes confuse students, and they think the answer is x squared times whatever that limit for, well, let's just look. The limit as x goes to 3 of f of x is 2. Okay, it's not x squared times 2. Right, that's not what this is. Is it possible for me to do that first limit? It's a type 1, right? It's a type 1. I'm just going to plug the 3 in. That's what you do. You just plug the 3 in. So you plug the 3 in and you get 3 squared. And now my job is just to simplify. So we've got what? 3 squared is 9. 9 times 2 is 18. And that's the third example on the limit law type. And I'm pretty sure you do have some limit law type on your homework as well. So whenever you see that kind of weird setup where they give you some values and, ask you to do stuff, this is a limit law kind of problem. All right, how are we doing? Okay, so now we've got some examples, just more practicing. We've got 4 different examples where we want to find each of the limits. We're just continuing to practice the concepts that we've done. Just try to get as many problems underneath our belt as we can before we head off by ourselves to our homework. So here we go. So first step, we plug the -1 in. That's the first step to every single limit. You plug, this is A, right? Whatever that value is A. You want to plug that in. So we get -1 squared minus 2 times -1 minus 3 over -1 squared minus 1. Let's see, what is that? That gives me 1 plus 2 minus 3, that's 0. In the bottom, we have -1 squared, which is 1. 1 minus 1 is 0. So this is a type 2. This is a type 2. This is an indeterminate form. Okay, so let's think back to the things that we could try. We're focusing on this. We're focusing on this function. What can I try to make that look different? Factoring. I should try to factor because it totally looks like I could factor the numerator and the denominator, right? So that's what we should do. That's the technique that we should try. So let's factor. Let's see. We've got the numerator x. Let's see. So the back sign is negative, so my signs are different. Let's see. I need to multiply to get 3 and subtract to get 2. That looks like what, a 1 and a 3. Does that look all right to y'all? And you're thinking, yay, we get to factor again. I know y'all miss it so much. The denominator is a special kind of factoring pattern. Do we remember what that is? Yep, x plus 1, x minus 1 is the difference of perfect squares. So this is x plus 1, x minus 1. Okay, do we see something that we can simplify? The x plus 1s, very good. So the x plus 1s are gone, so let's rewrite it, and then we're going to try it again. The limit as x goes to -1 of x minus 3 over x minus 1. Let's see, so that's -1 minus 3 over -1 minus 1. So what do we have here? -4 over -2, which is 2. So this time, 0 over 0 is 2. Okay, how we doing? Wonderful. This is actually your very first unit next year. You're getting a head start on next year. Yay. All right, let's look at the second example. Okay, so we're going to do what we do, which is plug A in. Okay, so this gives me negative 2 over, that'd be 2 minus 2 squared. And that's what, negative 2 over 0. Okay, this is type 3. This is type 3. What do we know for sure about this function? There's a vertical asymptote where? At 2. We know there's a vertical asymptote at 2. And I'm just going to, kind of give it's at 2. Just going to give us a visual. That's what we got going on. Now, what we want to consider is what is happening. We can do this graphically. If you know how to graph this function, you could graph it. If you don't, then we could do some numeric things. So as I'm coming from the right, I would want to look at 2.1. What if I plug in a 2 point, this is a numeric. I'm going to show you, this is a numeric way to do the limits from both sides. You can do it numerically or graphically. I'm going to look at it numerically. So if I look at a 2.1 and I basically do like negative 2 over 2.1 minus 2 squared, all I want to know is if I get a positive or negative number. That's all I want to know. Because I know that it's either going to go up or down, right? It's a vertical asymptote. I can't go through it. You can't go through it. So let's see, on the bottom I'd have a positive number, so that's going to give me a negative number. So that means that we are going down. Coming from the right, we're going down. Okay, so now we're going to come from the left, and notice that the best thing to do, let's just make ourselves a note. Get 1/10 away from A on either side. This will never go wrong for you for the type 3. This is a type 3. You want to get 1/10 away from A on either side. This is doing it numerically, which is typically what a faster way to do than fully graphing this. It's typically faster to do it numerically. So you want to go 1/10. So if my A is 2, which it is, I want to look at 2.1, and on the other side I want to look at 1.9. And I want to do the same thing. I want to plug in a 1.9. Let's see, and I'm only looking for the sign. So let's see, I have a negative on top. On the bottom I have a positive. This is going to go to this sign is going to be a negative number. So that means we're going down there also. So then what I can say is that this one tends to negative infinity. T-E-N-D, tends to, that's a fancy calculus word, tends to. That means it's headed towards. This is headed towards or tending to negative infinity. And notice that I'm not putting equals negative infinity. We don't equal something that's a concept. We only arrow to it. And this is a type 3. So we've done all 3 types now, 1, 2, and 3. The most common is type 2. This is a type 3. It's not that common. So it may be that you might forget this. So this might be something you want to pay special attention to, because type 3, this type is not that common. All right, questions so far? We okay? All right, so this is the uncommon type 3. where we get a number over 0 and we have to look from either side. I prefer the numeric way, which is the way I'm showing you, but you could totally graph that function and just look at it. Okay, let's go to our third example on this set. First thing, we're always going to plug in. We're going to plug in the 0. So we get the square root of 0 plus 3 minus the square root of 3 over 0. And that gives us, what does it give us? Square root of 3 minus square root of 3 is 0 over 0. Another type 2. That's our most common type. Okay, I want you to focus on this function right here. We've got to figure out what are we going to do to make it look different. Okay, if we think about the techniques that were suggested to us up at the top, we were told we could factor and reduce, and we've done that a couple of times. Does this look like a factor and reduce problem? No, not really. Not really. We were told we could multiply by the conjugate. Okay, that looks more likely, don't you think? Usually multiplying by the conjugate has to do with radicals. So that's the type that we're going to work on here. We're going to multiply by the conjugate over itself because we can only multiply by 1. This is not an equation. This is not an equation. We are not allowed to multiply by anything except 1. All right, so let's try the second thing they suggested to us, which is multiply by the conjugate. All right, so let's go over here. We're going to do the limit. The limit as x goes to 0, so our function is the square root of x plus 3 minus the square root of 3 over x. We're going to multiply by the conjugate, which is the square root of x plus 3 plus the square root of 3. Remember conjugate business, how the middle sign is opposite? The square root of x plus 3 plus the square root of 3. Okay, so that's our goal. We're going to multiply by the conjugate. Okay, we got this. So the limit as x goes to 0. All right, so we got to FOIL it, right? We got to FOIL the numerator. And we know we love the conjugate because outside, inside, you know, FOIL. Outside, inside, go to nothing. So it's basically first times last, right? Remember that back in the day? All right, root x plus 3 times root x plus 3 is basically x plus 3. Okay? Root 3 times root 3 is 3. Now the denominator, we do not want to multiply that out. Please do not do that. If you do that, you're going to miss the little present that's going to happen. It's a little present that's just buried there. Okay, so I'm going to pause here for a second and make sure we're okay. So the radicals, the times, you know, the conjugate, we have to multiply that part completely out, but the other part, don't do it. Resist the urge. All right, so let's simplify. So we know 3 minus 3 is, you know, nothing, 0. And we have x over x times root x plus 3 plus root 3. Do we see anything else that we can cancel? Yep, the x. We got the x on top and the x on bottom. Okay, so those cancel. So what that leaves us with is the limit as x goes to 0 of 1 over. Now, just because I canceled everything up top doesn't mean that there's nothing up there. That's not a 0 up there. I hope we all remember with our fraction stuff. That's a 1 up there. And on the bottom, I have the square root of x plus 3 plus the square root of 3. Now that's the limit that we're going to do. Now we plug the 0 in. I get 1 over the square root of 0 plus 3 plus the square root of 3. That is 1 over, let's see, 1 square root of 3 plus 1 square root of 3 is 2 square root of 3. And you do not need to rationalize in calculus. You're done with that. So now we've done a type 2 doing multiplying by the conjugate. How are we doing? Everybody okay? Okay. See how this is a beautiful combination of everything that you've learned? All the fraction stuff you've learned, the factoring, all the algebra stuff is embedded in calculus. The hardest thing about calculus is algebra, not calculus. That's just the way it goes. All right, last one. Okay, let's do our first thing. So we want to plug in. We're going to plug in the -3. So I have 1 over -3 minus 1 plus 1/4 all over -3 plus 3. Okay, what does that give me? That gives me 1 over -4 plus 1 over 4. That's 0. And -3 plus -3 is 0. Well, here we go. Another type 2. Again, that's our most common is type 2. You really need to show the 0 over 0, just like I'm showing. Even next year, you need to show the 0 over 0. Okay? That will typically get you a point on the AP test. Okay, show it. All right, so that means that we need to try something. So let's focus on this function right here. Let's think about the things we tried so far. Does factoring seem like something we could try with that? That doesn't seem very helpful, does it, factoring? I don't think so. Multiply by the conjugate? I don't see a clear way out to fix that up. What other things was a recommendation that we might try? Common denominator. This is a complex fraction, right? It's a fraction inside of a fraction. It would be to our benefit to make it a non-complex fraction. We've done a bunch of these, right? We find a common denominator, we keep, change, flip. That's what we need to do here. Oh, all the algebra. Yay. Okay, here we go. For algebra lovers out there, you're probably like, yes! For non-algebra lovers, I'm sorry, but that's kind of where we are. So we're going to -3. All right, so my common denominator on the top, let's see, I need to multiply, so 1 over x minus 1. I need to multiply that by 4 over 4. And then on 1/4, I need to multiply that one by x minus 1 over x minus 1. And the denominator is just, x plus 3. There's really nothing to do there. Okay, so that's just getting ready. We're just getting ready to take care of this business. All right, so let's work on our numerator. So x goes to -3. And just so you know, you really need to carry the limit statement with you. This right here is called the limit. I'm calling it the limit statement. This is the limit piece. You got to carry that everywhere. It's kind of like a little suitcase. It's telling you what to do, and you can't get rid of it until you've done what it says. All right, so please don't just get rid of it and then please keep it there. It gets really sad when you leave it behind. It gets really upset about that. All right, so let's fix this. So you've got 4 over 4 times x minus 1 plus, let's see, x minus 1 over 4 times x minus 1 all over x plus 3. Okay, that's just my common denominator step. Now we're going to add those fractions together. So what do we have? The limit is x goes to -3 of 4 plus x minus 1 over 4 times x minus 1 all over x plus 3. I try to make a really, the main fraction bar, which is the really big one, I try to continue to make it really big so I don't get confused on where the main fraction bar is. And we've talked about this before when we were working with these previously. All right, so now we're ready to keep, change, flip. So we've got the limit as x goes to -3. So keep the top. So let's see, 4 minus 1 is 3. So the numerator, I've got x plus 3 over 4 times x minus 1. Keep, change division to multiplication, and flip the bottom upside down. So 1 over x plus 3. Okay, so that's our keep, change, flip business. Does anyone see anything we can do to reduce this fraction? What can we do? Cross out the x plus 3's because it's a product. That's perfectly legit. If I was adding those, that would not be legit, but I'm multiplying them, it's legit. I can cross those out. So let's rewrite the limit so we can finish it up. So the limit is, so The limit as x goes to -3. So in the numerator, I'm left with a 1. In the denominator, I'm left with a 4 times x minus 1. All right, so here we go. We're going to plug the -3 in. 1 over 4 times -3 minus 1. Let's see, what is that? 1 over 4 times -3 minus 1 is -4. So my answer is -1/16. This time, 0 over 0 was -1/16.